Hello students, today we will discuss about electromagnetic induction. All of you know that if a charge Q is at rest, that means the velocity of this charge is 0. Then this charge create electric field, that means E. So if a charge is at rest, that means V equals to 0, then this charge create electric field. Now if a charge is moving with constant velocity, that means V equals to constant. So if a charge Q is moving with constant velocity throughout a conductor, suppose this charge is moving through this conductor, then this charge produce current. And if I place a current carrying wire, suppose the direction of the current is along this direction, then magnetic field is created around this conductor, along this direction. So with the help of current you can produce magnetic field. So with the help of current you can produce magnetic field. Now you have to know that is it possible to create current with the help of magnetic field? So you have to know that is it possible to create current with the help of magnetic field. In electromagnetic induction we have to learn the process and theory to create current with the help of magnetic field. All this chapter in electromagnetic induction we will discuss about the process and theory related to produce current with the help of magnetic field. So to start the chapter of electromagnetic induction, you have to know two physical quantities related to electromagnetic induction. One is magnetic flux, and another is magnetic flux density. Flux density. What is magnetic flux? Suppose this is a uniform magnetic field. Suppose I place a area of dA with this area has a vector quantity. The area is a vector quantity. So suppose this is a area. Then this area is a vector quantity, so it has both magnitude and direction. Suppose this vector magnitude is dA and its direction is always to the normal of the surface. Suppose this is a area and this area has a direction. The direction of the area follows the normal of the surface. That means the direction of the surface is along this direction. So this area vector can be written as the magnitude of the area and the unit vector along the normal to the surface. So I place a area on a uniform magnetic field with create an angle. Suppose this is a unit vector. That means the area creates angle with magnetic field is theta. Magnetic field is theta. Suppose the direction of magnetic field is along this direction and this is the area. Suppose I place this area like this. That means the direction of magnetic field along this direction and direction of direction of this area vector is along this direction. That means there is an angle between the magnetic direction of magnetic field and the area vector. This is the theta. That means what is theta? Theta is the angle between a vector, here dA vector and magnetic field. dA vector means the area vector. Now what is magnetic flux? Magnetic flux is equals to the total number of magnetic lines of force crossing normally to the area. What is, suppose this is the direction of magnetic field and this is area. If I place this area like this, then the magnetic lines of force cross this area. If I place this area in this way, then this area, the maximum magnetic lines of force cross this area, and this is normally. Suppose normally, that means here you have to mind it that the angle between area vector and magnetic field is theta. So the total magnetic flux can be written as d phi equals to, here the normal component of the direction is dA cos theta. That means B into dA cos theta. That means B dot dA. This is the magnetic flux. So total magnetic flux can be written as the integration of magnetic flux, that means integration of B dot dA. So the B is a constant uniform, so the integration of dA, if we integrate on dA, then the total area BA, here is BA cos theta, here suppose BA cos theta, because this is a dot product, so this will be BA cos theta. That means flux equals to BA cos theta. And if theta equals to 0, if theta equals to 0. That means if this is the area and this is the direction of magnetic field. If this area is placed like this, then the maximum magnetic lines of force cross this area. That means cos 0 degree equals to 1. That means maximum flux will be B into A. So if the area is placed perpendicular to the magnetic field, then the flux will be maximum. You have to mind it that perpendicular to the plane, but the angle between area vector and magnetic field will be 0. And if theta equals to 90 degree, then cos 90 degree will be 0. That means magnetic flux minimum value will be 0. So if I place this area in this way, then no magnetic flux cross this area. That is, the angle between area vector and the magnetic flux field lines will be 90 degree. That's why the minimum magnetic flux will be 0. Now you have to know the unit of the magnetic flux. There is two systems. One is CGS and another is SI system. So unit of magnetic flux. One is CGS unit and another is SI unit system. In SI system, the units of magnetic field is Weber, and CGS unit is Maxwell. The relation between the Weber and Maxwell is 1 Weber equals to 10 to the power 8 Maxwell. 10 to the power 8 Maxwell. 10 to the power 8 Maxwell. Now you have to know that what is magnetic flux density. Here you have already calculated that magnetic flux equals to B dot dA. If the angle theta, that means B dA cos theta. If theta equals to 0, that means B vector and D vector is parallel to each other. That means parallel. So it will be d phi equals to B dA. That means B equals to d phi dA. This is a magnetic flux density. What is magnetic flux density? If I place a unit area, that means here is dA is 1 unit area, then B will be d phi. If I place a unit area on a magnetic field, then the total magnetic lines of force crossing the unit area perpendicular normally, then that flux will be equals to the magnetic flux density. So what is magnetic flux density? Magnetic flux density, the flux, total flux for a unit area, So this is also called a magnetic induction. This is called a magnetic induction, or also called the magnetic field. Magnetic field. This is also called a magnetic induction or magnetic field. That means if I place a unit area normal to the direction of magnetic field, then the total number of magnetic lines of force cross the unit area is called the magnetic flux density. You have to know that what is the unit of magnetic flux density. Here, unit of magnetic flux density, unit of magnetic flux density. Here, B unit is the unit of magnetic flux, that means Weber, and the unit of area, that means meter square, that means Weber per meter square. Weber per meter square. Here the unit of magnetic field is Tesla, so Tesla equals to Weber per meter square. This is the relation. Faraday has three laws of electromagnetic induction. That is first law, here is second law, and third law. Third law, or also is called the Lynch Law. Lynch Law. This is the three laws of Faraday of electromagnetic induction. First law says the condition for creating electromotive force with the help of magnetic field. That means first law says the condition how you can create electromotive force with the help of magnetic field. This first law says this condition how you can produce electromotive force with the help of magnetic field. And second law says what is the amount of induced EMF generated with the help of magnetic field. That means second law express the amount of electromotive force. What will be the amount of electromotive force? And third law says the direction of electromotive force, force or force of EMF. This is the three laws of Faraday's. Now first law says that when the magnetic flux linked with the circuit changes induced EMF is produced. Induced EMF is produced. produce. That means if you change the magnetic flux linked with the circuit, then EMF will be produced. If there is no change in magnetic flux with the circuit, linked with the circuit, then there will be no induced EMF. That this is the condition. That means you have to change magnetic flux density linked with this circuit. This is the condition. If you change the magnetic flux linked with the circuit, then induced EMF will be produced. So how you changes the magnetic flux, how you can produce magnetic flux? That means suppose there is two condition. That means the process of changing magnetic flux. How you can changes magnetic flux? You know that magnetic flux phi equals to BA cos theta. Already you have known it. There is three quantities related to magnetic flux. So suppose this is a loop, and this is a bar magnet. If this bar magnet move along this direction, then there will be change in magnetic flux because there is a change in magnetic field. That means number one, by changing B vector, that means magnetic field, by changing magnetic field. So if this magnet moves towards this circuit or loop, then there will be change in magnetic flux. Or if this bar magnet moves away from this loop, then there will be a change in magnetic flux. If this is fixed and if this loop moves away from this magnet, then there will be a change in magnetic flux. Or if this loop moves towards the magnet, then there is a change in magnetic flux. That means if I change there is a relative motion between loop and bar magnet, then the magnetic flux will be changed. So that means if there is a relative motion between loop and bar magnet, then there will be a change in magnetic flux. So by creating relative motion between loop and bar magnet, you can produce induced EMF. Number two, by changing the area of the loop, the area of the loop. If you change this area of this loop, then there will be change in magnetic flux. So if there is a change in magnetic flux, then the induced EMF will be generated. This is the third condition. Second condition. Third condition, if you change this theta, means if you rotate this loop, then there will be change in magnetic flux. So if this rotation, if the you can by changing the angular velocity or angular displacement, angular displacement. So this is the condition for changing magnetic flux, and if you change the magnetic flux, then induced EMF will be generated. This is the first law of Faraday. Second law of Faraday says that what is the amount of electromotive force? Amount of electromotive force, that means induced electromotive force, is proportional to the change of magnetic flux. That means the magnitude of induced, the magnitude of induced EMF is proportional to the rate of change of magnetic flux, rate of change of magnetic flux. That means E proportional to d phi by dt. This is the second law of Faraday. This is the second law of Faradays for electromagnetic induction. That means second law states that what will be the induced EMF. That means induced EMF is directly proportional to the magnetic flux density. Direct rate of proportional is proportional to the rate of change of magnetic flux density flux. Then if there is a n number of turns, then it will be E is proportional to n d phi by dt. This is the number of turns. Now what is the third law? Third law says the direction of the EMF. Suppose this north pole is moved along this direction. You have to find out the direction induced EMF. What is the direction of induced current or induced EMF? You have to find it. With the help of Lynch Law, you can find out the direction of this induced EMF. So if this magnet is moved away from this circuit, then what will be the direction of induced EMF? To find out the direction of induced EMF, you have to know what is Lynch Law. Lynch Law states that the induced EMF is such as to oppose the cause that produces it. Third law or Lynch Law states that the induced EMF is such as to oppose the cause that produce it. What Lynch Law states that the induced EMF is such as to oppose the cause that produce it. You have to think about it. There is a cause and there is an effect. Effect is induced EMF. That means there is a cause and effect. Effect is induced EMF, induced EMF, induced EMF. And cause, what is the cause? Cause is change of flux. That means suppose this bar magnet moves towards this loop, then there will be induced EMF. That means the cause of the induced EMF is moving of bar magnet. That means change of magnetic flux, change of magnetic flux. This is the cause. So this law states that the induced EMF, direction of induced EMF is such a way that it opposes the further change of magnetic flux. So this third law, that means Lynch law, states that the induced EMF is such as to oppose the cause that produces it. That means here is cause is moving of the bar magnet. If you move the bar magnet along this direction or along this direction, then there will be a induced EMF, or induced EMF in such a direction that oppose the further change of magnetic flux. That means the direction of induced EMF such that it opposes the further movement of this magnet, Do you understand what is says that? You have to think about it. There is two line. One is EMF, induced EMF, and another is cause. What is the cause? Cause of induced EMF is moving of this magnet. If this magnet is moves towards this loop, that means there will be change of magnetic flux. So the cause of creating magnetic induced EMF is change in magnetic flux. So the induced EMF is such a direction that this induced EMF opposes the movement of this magnet. That means in such a way that this is North Pole, then it behaves like the North Pole. That means it will be anti-clockwise. Clockwise direction, so that this loop behaves like a N pole, and N pole repel each other. So the further movement of this bar magnet will be opposed. So this is the Lynch law. So Lynch law states that the induced EMF is such as to oppose the cause that produces it. So what is the cause? Cause is change of magnetic flux, that means moves of bar magnet. And what is the effect? Induced EMF. That means the direction of induced EMF is such a way that there must be a N pole, so that this N pole and this N pole to repel each other. So if the direction of this loop current or induced EMF will be anti-clockwise, then this loop will behave like a N pole, so that this N pole and N pole repel to each other. According to Lynch law, you can write that the induced EMF proportional to minus N dphi by dt. This minus signify that the induced EMF opposes the change of magnetic flux, magnetic flux. Now E equals to minus Kn d phi by dt, where K is constant. Here K is constant, and the unit of d phi by dt and E is taken such a way that K will be 1. So E equals to minus a d phi by dt. This is the Lynch laws of electromagnetic induction. Now you have to know what is the induced. This is the induced EMF, and suppose this is a circuit, this is a loop, this is a loop, and this is a magnet NS. So you have to find out the induced EMF, induced current, and induced charge and induced power. That means induced EMF, and what will be the induced current? Induced current, and here is induced charge. Here is induced charge, and here is induced power. Here is induced power. These four quantity you have to learn. You have already calculated that what is the induced EMF. Here is induced EMF equals to minus n d phi by dt. Now if this loop has resistance of R, then the current, induced current of this loop, suppose I, then I will be E by R. That means if you put the value of E, then you can get minus n by R d phi by dt. Now you have to find out the induced charge on this loop. Here you see that we know I equals to dq by dt. That means dq equals to I dt. So dq, induced charge dq, will be I dt. You have already calculated the induced current. Here you put this value, that means minus n by R d phi by dt, and here is also dt. dt cancel out, that means n by R d phi. Here you see that the induced current does not depend on time. That means induced current does not depend on time. And also if the total induced charge, if you calculate total induced charge, that means the integration of dq, then the integration of minus n by R into d phi, that means that will be q, and it here will be minus n by R phi. So both the condition here, the total charge on this loop cannot be greater or less, always same. The total charge on this loop always in same, only the velocity of charge will be differ. So because only if you change the magnetic flux, so there will be no addition of charge on this loop. So the total charge on this loop will be same. That means total charge or any loop, the total charge must be constant. Total charge must be constant. Here Induced power. What will be the induced power? Induced power equals to I square r. This is the induced power. You have already calculated the I, value of I. That means here the value of I equals to minus n by r d phi by dt whole square into r. That will be minus n square by r d phi by dt whole square. This is the induced EMF, induced current, and induced charge and induced power. Here you have to mind it that this component that means total induced charge does not depend on time, and also the total charge on any loop does not depend on magnetic flux or does not depend any other quantities, because you have used same circuit and the total charge on this circuit does not depend on any other quantities. Now you have to find out the direction. You have to find out the direction of induced current. What would be the induced current? Suppose if there is a loop, if this loop, suppose this is a loop, if this loop the current is anti-clockwise, yes, if the induced current is anti-clockwise, then this loop behaves like north pole. If a induced current direction is anti-clockwise, then this loop behaves like a north pole. If the induced current on a loop is along in this direction, that means clockwise, then this loop behaves like S pole, that means south pole. There is fourth situation, that means position of magnet. Position of magnet. Position of magnet. There is four position. Position 1. Suppose this is a loop. And here this is a bar magnet. Here is N pole, here is south pole, and here this is a observer. Suppose this bar magnet moves towards this loop. This is a one condition, and there is another condition is, suppose there is a loop, and this is a bar magnet, and there is N, here is south, and here is a observer, and this magnet moves away from this circuit. And here this is a loop and this is a bar magnet, because here is south pole and here is north pole, here is a observer, and this magnet moves along this direction. And here the fourth condition is, suppose there is a loop and this magnet south pole, here is north pole, here is observer, and this magnet moves along this direction. You have to find some quantities. That means direction of induced current, and pole, this is a loop behaves like what pole? That means south pole or north pole. And magnetic force, here is magnetic force, and the change of magnetic flux, here is change in magnetic flux. This is the 4 quantity you have to learn in this way. Here condition 1, when this magnet moves towards this loop, then there must be a north pole. So this north pole, this loop must behaves like a north pole according to the Lynch law. So it must be the induced current must be anti-clockwise. That means along this direction induced current must be anti-clockwise, because when the induced current moves along anti-clockwise, then this loops behaves like a N pole. What is the magnetic force? If this pole behaves like a north pole, that this north pole also a north pole, that means repulsive force. There will be repulsive force. And here the change of magnetic flux is increase. That means change of magnetic flux is increase. If you move this magnet towards this loop, then the magnetic flux will be increased. And here this loop behaves like a south pole, because if there is a south pole, there is a north pole, and south pole and north pole attract each other. So the loop behaves like a south pole, and it must be a current must be a clockwise, because when current flow in clockwise direction, then the south pole, this loop behaves like a south pole. So here will be a south pole and here is north pole. So the force is attractive. And here you see that this magnet moves away from the circuit. That means the change of magnetic flux will be decrease. And similarly, here you see that the south pole moves towards the circuit. That means this pole must be a south pole, that this will behave like a south pole. That means it must be a clockwise direction. That means induced current will be clockwise, and this will be a repulsive force. And also this magnet moves towards the circuit, that's why it will be increases. And here similarly, when this south pole, here must be a north pole, because this magnet moves away from the circuit. That means it must be a anti-clockwise. That means along this direction, and it behaves like a north pole. north pole, and here the attractive force will be attractive, and the magnetic flux again decreases. This is the theory for calculated the direction of the induced EMF. Direction of induced EMF in such a way that the change of magnetic flux oppose. The change of magnetic flux oppose. This is the laws of Lynch laws of electromagnetic induction. In this chart, you can, if you understand this chart, then you can calculate any direction of induced EMF.